Hello and welcome back to CMOS RF integrated circuits. So, we were discussing noise in the previous class and that is the module we are in, and today we are going to talk about noise in a MOSFET and how we model it. So, as far as I remember, we ended the previous class on this note that if you have a MOSFET, this is your MOS device, maybe there is a body, I am just omitting the body for convenience, it does not matter. The channel is really something which is like a resistor, it is like a wire which is filled up with electrons. All of these electrons are bouncing against each other, all of these electrons are jostling, fighting for space, right. So, the channel, I have tilted the channel in favor of the source against the drain, because typically the drain voltage is going to be larger than the source unless you are using the MOSFET as a switch or in its linear region. Even then the drain voltage is going to be larger than the source voltage unless you are using the MOSFET as a switch. So, we are not going to use the MOSFET as a switch, that is why I have tilted the channel in favor of the source, does not really matter. What matters is that this particular channel is filled up with electrons, and all these electrons are jostling for space, and they are jostling more as the temperature increases. So, as the temperature increases, they are jostling more, presumably kT, right. Boltzmann's constant is going to be involved in this, because you know that is the degree of freedom business. In your statistical thermodynamics, all the degrees of freedom will get equal energy and so on and so forth. Okay. So, this particular channel is modeled as the channel in shunt with a noise current source. Okay, remember that the noise current does not really have a direction. Why did not I put a voltage source in series with the channel? Because it is hard to do that. Okay. It is hard to do that, and you are now getting within the dynamics of the MOSFET. So, you have to break up the MOSFET, it becomes difficult to analyze. So, instead it is easier to just place a noise current source in shunt with the channel. Now, this noise current I n squared, mean square noise current, is going to be proportional to kT, right. It is also going to be proportional to the number of electrons available in the channel. Qi is the inversion charge. So, it is going to be proportional to the number of charges, number of electrons present in the channel, right. So, you can model this particular noise over all regions of operation with a formula that looks like this, kT times Qi, and then there are some other factors involved, right. This can be done. This works over all regions of operation, but Qi is really not something that you would like to work with, right. For a MOSFET, you do not really want to work with Q, the channel charge. You would rather work with a width, a length, mu, Cox. You would rather work with transconductance, right. You would prefer not to work with the channel charge. It is really a parameter, that is a quantity that is within the MOSFET. You do not have direct access to the channel charge, you cannot measure channel charge directly. So, that is why, even though finally in the heart of it this is what it is, we would prefer to model the noise in terms of higher level parameters, and really the channel charge is proportional to GM, is not it? The larger the GM, more the channel charge, larger the transconductance, more the channel charge. So, the channel charge is really proportional to GM. So, instead of the channel charge, you can say that it is also proportional to GM. Now, what you can work out is basically from the fact that there are these electrons in the channel, you can work out that under conditions of strong inversion and saturation, when the channel is pinched off, so it is tilted, the channel is tilted in favor of the source, right. So, you can find out all these areas and so on and so forth, and the end result is something like this: I n squared is equal to 8 by 3 times k T times G m df. Okay, this is the end result of all the analysis that you would want to do, and this by 3 is really coming, 8 by 3 factor is really coming from the fact that the channel is tilted in favor of the source against the drain, right. So, that is where this by 3 factor is coming from. If it had been a uniform channel, then you would probably have got 4 k T G m d f, I do not know. Okay. So, this is I n squared under conditions of strong inversion and more importantly under saturation. Okay. It is possible to build a MOSFET noise model that works over all regions of operation, and there you are going to use this channel charge, you are not going to use this particular 8 by 3 k T G m d f formula in that case. So, supposing you are in weak inversion, supposing you are not in strong inversion, supposing you are not in saturation, all of these conditions are taken care of if you use a derivation based on the channel charge. Now, I am not going to do that, we are going to stick to this. Presumably in RF integrated circuits, you would want your device to be in strong inversion, otherwise you will not get the maximum FT. Most probably you are not working in under any other conditions, you are working under strong inversion. And if you are making an amplifier, I mean this noise is important when we are talking about a low noise amplifier, etc. So, if you are making an amplifier, it is likely that you have put your device in saturation, I mean most probably that is what you have done. So, strong inversion and saturation is good enough for this particular course. So, that is what we are going to stick to. Right. So, this gives me a model of the noise current in shunt with the channel. Now, in addition to this, what are the other sources of noise? There are few more sources of noise. One is the fact that the gate has some resistance associated with it. Really, you have a gate that is not really made up of metal. So, maybe the contact is over here, and when you let us say set a voltage on the gate, let us say you put a pulse voltage, you apply a pulse voltage, all of this charge has to travel through considerable amounts of resistances to reach, to spread around all over the gate, right. And the gate is not made up of metal, it is made up of polysilicon. All modern processors, the gate is no longer made up of metal. So, as a result, now it so happens that polysilicon is also the same material that is used to make resistors. So, the gate material is resistive, and as a result you are going to get a resistance, right. You are going to get an effective resistance as far as the gate is concerned. Now, this resistance, whenever you have a resistance, you can think of electrons jiggling around because of temperature, and when they are jiggling around because of temperature and there is resistance, it is going to cause a voltage, right. So, therefore, the gate has some random noise voltage on it. It develops a random noise voltage because the material is resistive, and that can be modeled as 4 kT times it is a resistance. So, you model it in this fashion, it is possible to model it in this fashion, right. Then there is also the substrate. Now, I am putting the body contact over there, but the body contact is really not there, the body contact is somewhere else. Okay. Suppose you have put a ring of body contacts around your transistor. So, this is how it is going to, that is called a guard ring, just by the way. It is good to do that because that reduces your substrate resistances, we will see how. So, the body sees a resistance which is marked by the resistivity of all of this, it is a distributed resistance. So, on the top view, if I have got my MOSFET, so suppose this is my MOSFET, and around the MOSFET I have made a set of body contacts. These are, this is the region over which I am making body contacts. It is called a guard ring. It is a very commonly used layout practice when you are designing RF integrated circuits. Okay. So, this is covered with metal, this guard ring is covered with metal and it is grounded. Okay, if we are talking about an NMOS, it is grounded, if we are talking about a PMOS, it is connected to the power supply. Okay. What is this doing? This is making sure that the entire region in between is also at the potential that you want. Do you remember Laplace's, how to solve Laplace's equation, etc., etc.? You remember Laplace's technique? You know, del squared V is equal to 0. So, ways to solve del squared V equal to 0. Del squared V equal to 0 is a fundamental equation in electrostatics, right. And ways to solve del squared V equal to 0 are basically solutions of Laplace's equation. There is the method of images, there are all kinds of different methods, etc., etc. And when you studied that, I refer you to probably book named Electrodynamics by David Griffiths. Right. Prentice Hall, as far as I remember. Okay. I refer you to that. When you saw, this was chapter 2 probably, chapter 2 or chapter, yeah. Okay. So, there is a lot of material about how to solve Laplace's equation del squared V equal to 0, and some of the common problems that are solved in this particular textbook. This is a classic textbook, and some of the common problems solved are when you have a grid which is all equipotential. So, let us say these are all metal structures, all connected to 0 volts, right. You can show that the entire region is going to be 0 volts. So, the entire region which has that grid is going to be at 0 volts. So, everywhere in between you are also going to get 0 volts most likely. You are going to get other things also, but to a great deal of approximation you are going to get 0 volts. Okay. So, this guard ring technique is basically something that we have borrowed from there. So, you put a grid around your device and hope for the best. You hope that inside the device all over the place you have got a body potential which is equal to 0 volts. Okay. So, this is something borrowed from there, and unfortunately it is not going to be exactly 0 volts, okay, because of resistivity within the body itself. So, the body itself is resistive, okay. The body itself is resistive, and because of this resistivity there is, because of this resistance there is going to be some noise voltage on the body. Surprise, we will have a noise voltage, right. How much is that noise voltage going to be? If I say that I succeed in lumping the body resistance as a resistance of a particular value, then that is again, that lumped noise voltage squared is again going to be 4 k T times that particular resistance times df, when we are looking at the noise over a certain bandwidth, right. So, this is basically the story, this is how we are going to deal with it. Similarly, if you have a contact resistance on the drain, a contact resistance on the source, then those also will add certain amounts of noise voltage. Okay. So, we will treat all of those like resistors. Now, when you are treating all of these like resistors, do not forget the parasitic capacitances that you have, okay. Do not forget those are important, because a lot of this noise is going to get filtered out by the parasitic capacitors. So, there is a CGD, do not forget about it. There is a CGS, do not forget about it. There is capacitance between body and source, there is capacitance between body and drain. Okay. So, please make sure that all of these capacitors are there, all of these, place all of these noise resistors, noisy resistances, and work your way. Okay. Now, when we deal with noise, there are so many different noise sources, it is very hard to do the analysis in one shot. So, what we normally do is we use the principle of superposition and we analyze one noise source at a time and find the effect at the output, right. And then finally, once we are done analyzing one noise source at a time, we sum up everything together and find out the total noise. Now, here there are two important things, two important definitions. One is the output noise and the second is the input referred noise. So, suppose you have a system which is filled up with noisy elements, noiseless elements, it is some general circuit and this is the output. Then you take each noise source one at a time, find out its effect at the output, sum everything together, that will give you the total output noise. Okay. Now, the input referred noise is something that is harder to understand. There is nothing, there is no great definition for output noise. Output noise is the total noise that you see at the output. Now, you do this exercise, you find out the output noise and you consider your system having an input and you have your output. Right. You find out the total noise at the output, basically you take each noise source one at a time, find its effect at the output, sum up everything together, that gives you the output noise. Now, the question is, assume that all of these noise sources are not there, that is, assume a perfect noiseless system. Right. The question is, what should be your voltage or voltage squared at the input, what should be the value of the voltage or voltage squared at the input such that you get the same voltage or voltage squared at the output as before. Before is the output referred output noise. So, your target is to get the output noise. What should be your input such that you get the output noise through a noiseless network? Okay. If you say that the output noise was so much V out squared per hertz, let us say 1 nanovolt squared per hertz, okay, that was your output noise, and let us say the gain of your system is 10, then what should have been this voltage? You want to get 1 nanovolt squared per hertz, okay, gain of your system is 10. So, what should have been the input had the noise not been generated within the circuit at all? What should have been the input? Right. Okay. So, this is called the input referred noise. You basically find the output noise and divided by the gain squared. So, you find out the mean squared noise voltage at the output divided by the gain squared, that should give you the mean squared noise voltage at the input, which corresponds to the same noise mean squared noise voltage at the output. So, that is the input referred noise. This is the definition of input referred noise. Okay. Now, before we start off with the next set of definitions, how are you going to find out let us say this is your circuit. MOSFET is in strong inversion and saturation. Okay. Does RDS produce noise? Is RDS a noisy resistor? No. Okay, RDS does not produce noise. RDS is not really a resistor. It's not, there is no real resistor over there. It is because of the it's because of velocity saturation in the channel, correct. But there is no real resistor over there. So, be careful about it. Okay. Do not start putting noise sources because of RDS, just caution. So, suppose this is your system. What is the input referred noise of this? This is my input. Do I need to worry where the output is? Should not matter where the output is. The input referred noise is going to be the same. Fine, this is my output. So, we have a few noise sources over here. First, we have the noise of the resistor. Noise of the resistor can be modeled as the resistance in shunt with a noise current okay. And then there is the noise in the channel of the MOSFET, that also can be modeled as a noise current. Right. Let us forget about the gate noise for now. Let us forget about the gate noise, that is the noise because of the gate resistance. Let us forget about it. So, let us say this is it. Now, what is going to be the story? What is the total output noise? So, you take each noise source and find out the voltage that produces at the output. So, I have got a noise current 8 by 3 kT GMDF. I have got a noise current over here, this one is a noise current, and the voltage it produces at the output is the current times the impedance of that node, right. The impedance at that node is R parallel RDS. So, I times R parallel RDS is going to be my voltage. Now, I am not dealing with a current, I am dealing with a mean squared current. So, the mean squared voltage is so much. Okay, this is for the channel noise, and similarly for the resistor noise, they are both looking very similar, they are the same place in fact. These two come in shunt with each other. Okay. So, the total noise is so much. So, let me just take 4 kT out of the picture. Right. Now, of course, this is at DC, I completely threw out all of the capacitors that were there, let them be. I mean, once you put in the capacitors, the calculation becomes far more complicated, and you get your result in terms of the capacitors in fact, most probably. All right. Now, the question is, what is the input referred noise? What is the input referred noise of this? So, the gain of this is GM times R parallel RDS, that is the gain. Right. So, if I have to get so much voltage at the output, then I have to apply so much voltage divided by the gain at the input. Okay. And what you are going to get is this is what you are going to get. Okay. In other words, I am going to rewrite it. In this fashion. Now, one of these is coming because of the channel, the other is coming because of the resistor. Which is coming because of the channel? And which is this is coming because of the resistor. Okay. So, what do you see over here? The channel noise current, mean squared noise current, was so much. Okay. What I can do is I can rewrite this, remodel this as if I had a voltage on the gate. If I apply a voltage on the gate, that will generate a current in the channel. If I apply a noise voltage at the gate, I will get a noise current in the channel, GM times that voltage is the current, right. So, if the noise current is so much, then the noise voltage that I applied at the gate